Hello everybody, and welcome to this, the 12th logic lecture of Comp 0003. In today's lecture, we're going to finish the material on proof by induction. Over the last three lectures, we first began by reviewing the principle of ordinary induction over the natural numbers. And then we saw that the principle can be generalized in the sense that for any structure, such as lists or trees with an inductive definition, we can give a principle of structural induction over that definition, which allows you to deduce universal properties about those structures. So we can say that something is true of, for example, all lists, if we can show that the property is true no matter how we choose to build up the list, which is to say it should be true of the empty list. And also, if it is true of an arbitrary list, then it remains true when we add an element onto the front of it. And then we went on, I think, just at the end of last lecture to the idea of alternative induction schemes for different structures. And in fact, we're just for the natural numbers, we covered the idea of two-step induction, where the induction goes up not in single numbers, but somehow in pairs of numbers. So to show that a property is true for all numbers, you can show that it's true for the first pair of numbers, 0 and 1. And that if it is true for a pair of successive numbers, k and the successor of k, then it must be true for the next number after that, successor of k, or k plus 2. And then you know that since, if you think of it again as dominoes, every pair of dominoes knocks down the one after it. Then since we knock over the first pair of dominoes, we knock over number 2, I guess. And then since we know that if we can knock over 1 and 2, we can knock over 3. And so, and since we can knock over 2 and 3, we can knock over 4, and so on. Now, you might think that this is somehow a slightly different principle than standard induction on numbers, or you might think it's more powerful because you get to assume the induction hypothesis for a pair of numbers. Or you might think that it's maybe not quite as powerful because you have to show two base cases, 0 and 1. In fact, the first thing I want to do today is show that ordinary induction and two-step induction are somehow the same thing. They are equivalent in power, in that anything you can show by ordinary induction, you can also show by two-step induction and vice versa. So you don't gain or lose any power by using one or the other. After that, we're going to look at some different kinds of induction, most notably the idea of infinite descent, which is a kind of backwards induction on the natural numbers. And that's sometimes a bit non-intuitive, but it's very interesting. And then I'm going to turn the principle of infinite descent around and describe something called complete induction, where in order to show the property of a particular number, you are allowed to assume the property for all the preceding numbers, not just the one before or the two before or something like that. So first of all, I'm going to go to the slides and we'll look at the equivalence of two-step and one-step or ordinary induction over the natural numbers. And then I'm going to come back and we'll talk a little bit about infinite descent. So let's go to the slides and I'll see you in a bit. Okay, so let's first briefly recap the idea of two-step induction on the natural numbers. So two-step induction on the natural numbers says that if you want to show that some property P holds of all natural numbers, you can proceed in the following way. First of all, we'll show that P is true of 0, and we'll also show that it holds of the successor of 0. So we're going to show two base cases that the property P holds for 0 and 1. Then our induction hypothesis is that P holds for a pair of successive numbers. So for some arbitrary number k, we assume that P holds both of k and the successor of k. And then the step case of the induction is to show that P holds then for the next number after that, which is the successor of k, or k plus 2. So written as an inference rule, we have three premises. P of 0 and P of s of 0 are two base cases. And then we show that if P of k and P of s of k, then P of S of K, where again K is an arbitrary number. We assume that it's a natural number, but we don't assume anything else about it. And then the conclusion is that P holds for all natural numbers n. It holds of 0 and 1 by the base cases, and then by applying the step case here, we know that it holds for 2, and then since it holds for 1 and 2, it must hold for 3, and so on and so forth. Now, as a matter of fact, we can show that if we have two-step induction, then we can derive, or we can show the correctness of the ordinary induction principle. So here I've written, again as an inference rule, the schema or the rule for ordinary induction on n. So we just show one base case P of 0, and that if P holds of K, then it holds the successor of K, and the conclusion is that P holds for all natural numbers n. So if I want to show that the ordinary induction principle is correct using two-step induction, I'm going to assume the two premises of this induction rule, and I'll show that I can derive the conclusion, which is for all natural numbers n, Pn, by going by two-step induction. So I'm going to assume the two premises of the rule, P of 0 and Pk of P of S of K for any K. Those are because that's what is given to us by one-step induction, and I'm going to show by two-step induction that P holds of all natural numbers n. Okay, so two-step induction, remember we have to show two base cases. The first of these is that we have to show that P is true of 0. Now we already know that P is true of 0 because it's already given to us as the base case of the ordinary induction, which we have assumed. We also have to show that P is true of the successor of 0 in two-step induction. But we can see that from the premises of one-step induction that it is. We have P of 0 by assumption, and we also have that P of K implies P of S of K for any K by this assumption here. So if we take K equals 0, we have that P of 0 implies P of S of 0. Since we have P0 and P0 implies P of S of 0, well, whenever we have A and A implies B, then we also have B. So we have P of S of 0 as well. Finally, not finally, our induction hypothesis is going to be that P holds of two successive numbers, X and the successor of X, because that's the induction hypothesis that we're allowed to take in two-step induction. And we have to show that P then holds for the next number, which is successor of X. Now, that follows from the fact that we have P of K implies P of S of K by assumption for all K. So if we take K to be S of X, then by substitution we have P of S of X implies P of S of X. But we already have PSX by the induction hypothesis. We have PSX by induction hypothesis, and PSX implies PSSX by the assumption. And so again, by the so-called modus ponens, or A and A implies B, then we have B. So we have P of S of X. So we've established the two base cases of the two-step induction, and we've also established the step case of the two-step induction. So by the two-step induction principle, we have that P holds for all natural numbers n, and that's exactly what it is that we wanted to show here. So just by using the principle of two-step induction, we've managed to show the correctness, or derive the fact that the ordinary induction principle, the one-step induction principle, is valid as well. Now, you might think that somehow that's a bit easy because you think that two-step induction perhaps is more powerful, but actually it's not true. Here's the two-step induction principle written down again as an inference rule. So again, we have the two base cases, P of 0 and S of 0, and we have the step case which says, assuming P of K and P of S of K show that P holds of S, S, K. And then the conclusion is that P is true for all natural numbers n. So we're going to show that this principle is correct, but we're only going to use ordinary induction to do it. So we're going to assume that these three things, the three premises of two-step induction, are true. So we're going to take them as assumptions. And we're going to show that P holds for all natural numbers n, but we're only going to use the principle of one-step induction. Now, I'm actually going to use a trick here, which is sometimes called generalizing the induction. So although what I want to show is that P is true of all natural numbers n, I'm actually going to show a stronger statement. I'm going to show just by ordinary induction on n that P holds of n and its successor for all natural numbers n. So the actual statement that I'm going to show by one-step induction is that for all n, Pn and P of S of n. Now, obviously, if I have Pn and Psn for all n, then I also have Pn for all n. So in the base case, what I have to show, if I want to show this statement, remember I have to show that this is true for the natural number 0. That's what the base case of ordinary induction says. So what I have to show is that P0 and P of S of 0. Now, that's immediate because we've already assumed that P holds of 0 and P holds of S of 0. These are the two base cases of the two-step induction. So we have both of these already as assumptions. So the base case is proven. For our induction hypothesis, we have to assume that the statement P is true of some arbitrary number, and I didn't want to use K again so as to not get confused with the assumption, so I've taken X. So the induction hypothesis, corresponding to this statement here, is that P holds of X and P holds of S of X. In the step case, we then have to show that the same statement is true of successor of X, which means that what we have to show is that P holds of successor of X and P holds of successor of X. Well, the first conjunct is trivial. We've already assumed P of S of X, so that's no problem. So the only thing then is to show P of S of X, but this is also quite easy to do using the step case, using this third assumption of the two-step induction principle. So we have P of S of X we have Px and Psx by the induction hypothesis, and if we take K equals X in this rule here, we have P of X and P of Sx implies PSSX, so then we have PSSX as well. So we're done. So just to kind of restate again, we've shown here the correctness of two-step induction, meaning that if all the premises are true, then so is the conclusion, and we've shown it only using the proof principle of ordinary induction on the natural numbers. And since ordinary induction can derive two-step induction, and two-step induction can derive ordinary induction, the conclusion is that they must be completely equivalent as proof principles. Anything that you can show using one principle, you can also show using the other one. So now I wanted to introduce the idea of infinite descent over the natural numbers. Now previously, when we've considered induction for the natural numbers, to show that a property is true of all numbers, we've relied on the idea that we must show that it is true for the smallest number or numbers, and if it is true for some arbitrary number or numbers, then it is true for the next number. Now somehow infinite descent relies on just the opposite idea. So we actually show that if a property is not true for some number, then there must be some smaller number of which it is also not true. And that means that by repeating this reasoning, we construct, in fact, an infinite chain of natural numbers, each one smaller than the last, each one of them not having the property in question, and starting from some kind of finite point. However, you actually can't make a natural number, you can't decrease a natural number from a finite natural number infinitely often. So we end up with a contradiction. And so our initial assumption that some number does not have the property must in fact not be true, and so in fact we must obtain that all numbers do have the property. Now, this kind of relies on two main ideas that I think are both familiar ideas, but I think it's worth going over them again both now. The first is the idea of non-contradiction, or sometimes proof by contradiction. So if by making some assumption and then making deductions from that assumption, you arrive at a contradiction, which is impossible, you arrive at something impossible, then you know that that assumption in fact must have been false. If by assuming something you get to a contradiction, then your assumption must have been wrong. So as an example of this, actually it comes up in your murder mysteries all the time. Supposing that that somebody is shot in Glasgow, shot and killed between 10 and 11 o'clock on a Saturday night, and supposing that that person is one of my many mortal enemies, so I've got a strong reason for wanting that person dead. And supposing that the police come around to my flat and they actually find the murder weapon, the gun that was used to shoot the guy in my flat, well, then you might think they're quite reasonable to assume that I'm the murderer, I'm the person who shot the guy. However, if it comes out at a later date that on that Saturday between 10 and 11 I was not in Glasgow, but I was definitely here in London, then you realize that assuming that I am the murderer requires me to be in two geographically quite distinct places at once. So I have to both be in London and not in London at the time of the murder, and that's impossible. So the only kind of possible conclusion is that I cannot have committed the murder myself after all. Perhaps I was an accomplice or something, but for sure I definitely wasn't in Glasgow pulling the trigger on that Saturday night. So that's the first idea, the idea that any assumption that leads to a contradiction must be incorrect. Now, the second idea is that we have the idea that the natural numbers or other kind of structures that are inductively defined are what is called well-ordered. So we have an ordering on numbers, and moreover, we kind of have like a smallest number or numbers past which it is impossible to decrease. So as an example, I have here a bag of caster sugar. There we are. And you can see that there is made of many grains. I don't know how many grains of sugar are in this bag, but I mean, for sure it's a lot, but only finitely many. So supposing that I make the claim, at some point I'm going to need more sugar. Now that's a correct claim, and we can prove it by infinite descent using the following kind of idea. Supposing that I'm not ever going to need more sugar. So this amount of sugar, let's call it S. There's S grains of sugar in this bag, and we'll assume that's going to be enough. So I'm definitely going to have a cup of coffee at some point. My coffee is going to require a non-zero amount of sugar, at least one grain, probably many more. I don't know how many grains of this sugar are in a teaspoon, but certainly some number. Now, having removed that 1 teaspoon of sugar from my bag of sugar, there's then going to be a smaller amount of sugar, S prime. And S prime, I guess, also must be enough sugar. So I will never run out of sugar at S implies that I will never run out of sugar at S prime. But that means that if I take another spoon of sugar out of the bag, then that will also be enough, and another and another and another and so forth. And I'm kind of assuming that that will always be enough. But now that leads us to the idea that no matter how much sugar I remove from this bag, there will always be enough for a cup of coffee. But we know that I cannot remove non-zero amounts of sugar from this bag infinitely often. So that leads me to the conclusion that in fact my assumption that this will always be enough sugar, this amount, must have been wrong in the first place. So the conclusion is that this is not enough sugar, and therefore at some point I'm going to need to get some more. So now let's go to the slides again and see if we can make these ideas a little bit tighter. So although infinite descent was in fact known already to the ancient Greeks, the first person to really to isolate it as a proof principle and give it a name was the chap in the picture here, who's Pierre de Fermat, who's a 17th century French mathematician, most famous, of course, for Fermat's last theorem, which he scrawled in the margins of one of his manuscripts and then occupied the attention of mathematicians for a very long time afterwards, until it was finally proved by an Oxford mathematician, Andrew Wiley, I believe, in the I think in the early part of this century, sort of either in the 90s or the 2000s, so recently. I recently read a couple of books on art history, and certainly one of the points I was interested to kind of read up on is that if you look at a portrait of somebody, from history, then really that portrait tells you as much about what the artist thought of the subject as what the subject thought about themselves, or even what they sort of physically look like. And I think you can definitely tell from this picture here that probably the artist considered Pierre de Fermat kind of an arrogant bastard. And indeed, he had that reputation. I mean, he was very famous for refusing to reveal his mathematical methods, but or the proofs of his results. But he would sort of write to his peers, his other famous mathematicians, and kind of taunt them with the news of his discoveries and challenge them to do better. So here's an extract from one such letter that he wrote to one of his peers or friends. Because the ordinary methods now in the books were insufficient for demonstrating such difficult propositions, I finally found a totally unique route for arriving at them, which I called infinite descent. Now, of course, he was French, and of course this was originally known by its French name, descente infinie. So, this is an example he sees giving of an argument by infinite descent. If there were any integral right triangle that had an area equal to a square, there would be another triangle less than that one which would have the same property. Now here, when he says integral, he means that the sides of the triangle have got integer length, and by a right triangle he means a right-angled triangle. So, a right-angled triangle with integer sides and with an area equal to a square, so the square of another integer. So if there were a triangle of that kind, then there would be another triangle less than that one, i.e. with a smaller area, which would have the same property. So it would also be right-angled, it would also have integer length sides, but it would be smaller than the first triangle. Now, it is the case that given a number, there are not infinitely many numbers less than that one in descending order. He says, I mean always to speak of integers, but he also doesn't mean negative numbers, so we're talking about natural numbers here. So, yes, it's true. For any particular number, we cannot decrease it infinitely many times before we hit zero. Whence one concludes that it is therefore impossible that there be any right triangle of which the area is a square. And that's true as well. So, given this statement, which he does not prove, if you have an integer length right triangle with a square area, and given that you can then construct another one which is smaller, then there must be another one smaller than that, which also has integer length sides and has a square area, and so on ad infinitum. Now, just in the same way that you cannot decrease a natural number infinitely often, you also cannot write down infinitely many triangles starting from some initial one with natural number length sides. So you cannot make those triangles smaller and smaller forever, but this implication says that you can. So the only possible conclusion is that the assumption of the original triangle, the first one, that had a square area, must be false. So let's formalize this as an induction rule, or as an inference rule, I should say. So it is the case that given some natural number n0, there is no infinite descending chains of numbers n0, n1, n2, n3, so on into infinity, with each one being smaller than the last. So given some n0, I cannot decrease it infinitely many times, and at least not without hitting 0, and then of course at that point it's impossible to decrease it anymore. So the principle of infinite descent, I've written it in modern notation, is this inference rule here. So we want to show, as for all of these induction examples, that some property P holds of all natural numbers n. So we're going to proceed by contradiction. Supposing that it's not true, if Pn is not true for all natural numbers n, then there must be at least some number k such that P is not true of k. So k is a counterexample. If you have some general statement for all n Pn and you say it's not true, then there must be a counterexample, and let's call that counterexample k. Now, what the infinite descent step is, it says, assuming that P is not true of k, so not P of k, then show that there exists a k prime, which also is a natural number, by the way, such that k prime is smaller than k, and P is not true of k prime either. So that says, in other words, if there is a counterexample, k, to the conclusion, then there also must be a counterexample which is strictly smaller, the k prime, which is less than k. Now, since k is arbitrary in this premise, so we have our initial counterexample k, we construct a smaller counterexample k prime, and then we can just apply this rule, this fact again to keep going. We'll get another counterexample k double prime, which is smaller than k prime, and another one k triple prime, which is even smaller than that. And by repeating in this way, we conclude that there must be an infinite descending sequence of natural numbers beginning from k. K is bigger than k prime, which is bigger than k double prime, and bigger than k triple prime. And all of them do not have the property P. So just to say, since we know that P is not true of k prime, we have not P of k prime, and that's how come we can apply this rule again to get another smaller counterexample. So the premise says for any counterexample there is a smaller counterexample, and therefore there is an infinite descending chain of counterexamples. Now that's a contradiction because we can't decrease a natural number beginning at k infinitely often, and since we have a contradiction, what have we assumed that was wrong? Well, the only assumption we made was that the initial counterexample existed. So that can't be right. So k cannot after all be a counterexample. And so since there's no counterexamples, P must hold for all natural numbers n. Let's see an example of this. Now, I think we already showed by induction on the natural numbers, I think a standard induction, that every natural number is either even or odd. But just as an easy example, let's turn around and prove the same thing by infinite descent. Now, infinite descent says to show that some property P, which is the property of being either even or odd, is we want to show that it's true of all numbers, which is correct. But infinite descent says, suppose that it's not true for contradiction. So suppose that some k is a counterexample, meaning that it's not the case that some k is either even or odd. So we have a natural number, but it's neither even nor odd. Now, since it's neither even or odd, that means that it is both not even and not odd. Remember your De Morgan laws that says not A or B is the same thing as not A and not B. So k is not even and k is not odd. Now, since 0 definitely is an even number, and we have that k is not an even number, then k cannot be 0. It must be bigger than 0, which means that it's the successor of some smaller number k prime. Now, we have k is equal to successor of k prime. and k is not even and k is not odd. So since successor of k prime is not even, then k prime itself cannot be odd, because if k prime were odd, then the successor of k prime would be even, and we know it is not. In a similar way, since the successor of k prime, which is k, is not odd, then k prime itself cannot be even. If k prime were even, then its successor would be odd, and we know it isn't. And therefore, we have that k prime is not even, and k prime is not odd, and then by applying our De Morgan law again, we know that that means that it's not the case that k prime is either even or odd. But now k prime is a smaller number than k. So we have a counterexample, a number which is neither even nor odd, and by assuming the existence of that counterexample, we have managed to find a smaller number, in fact, just the number right before it, that cannot be even or odd either. And then by continuing this reasoning, we would be able to find another number, I guess actually the predecessor of k prime, which is neither even or odd as well, and so on and so forth. So given k, which is neither even or odd, we would actually find that none of the numbers before it can be even or odd either. And so we would end up building this infinite descending chain of counterexamples, again, k, k prime, k double prime, k triple prime. And we know that it is not possible to decrease the natural number infinitely often starting from k. That's a contradiction, and so our original assumption of the counterexample must be incorrect after all. So k cannot be a counterexample, meaning that all natural numbers are either even or odd. But of course, you can see as well that in fact we've just established what is to be established, which is assuming that our property P is not true of k, then there is some k prime, which is smaller, and such that P is not true of k prime either. That's what we have to show in an infinite descent. So here's another representation of the proof of that example as again a proof tree, which is something called a cyclic proof, which was my own specialty in my PhD thesis, and I've written a few papers on it as well. So our turnstile that kind of goes in the middle here, you can kind of think of it as an implication, if you like, but it sort of means assuming the left-hand side, the right-hand side is true. So we're assuming that for an arbitrary k in the natural numbers, that k is either even or odd. And then we kind of reason backwards by saying, well, there are two cases. If we can show that the case when k is 0 is correct and k is the successor is correct, then we know that we've covered all cases for the number k. So like doing a case split in an ordinary mathematical proof. So we have two cases on k. When k is 0, then it's definitely even or odd, and we're done. Otherwise, we have that k is the successor of some k prime. And although I haven't written that down, I've written down instead the more useful fact for infinite descent, that k prime is less than k. So we have that k prime is less than k, and we need to show that k is either even or odd, which is to say that the successor of k prime is either even or odd. Now, since odd of k prime implies even of sk prime, this reduces to showing that either k prime is odd or the successor of k prime is odd. And since successor of k prime is odd if k prime is even, this reduces again to showing that k prime is odd or k prime is even. And so we can see that actually this, apart from the commutativity of disjunction, is exactly the same thing that we started off having to prove. But so we can actually think that this proof tree is really an infinite proof tree, where I've taken this whole tree and sort of pasted it here, but now for the smaller thing k prime. So if you did this over and over again, you would actually get an infinite proof tree with lots of these even branches up the left-hand side and one infinite branch up the right-hand side. So if we were to assume that this thing is false, it means that the assumptions are true, but the conclusions are false. So by going round, so either we end up in in this branch and we're done, or we end up going around the right-hand branch over and over again, and we're going to get smaller and smaller numbers, k, k prime, k double prime. So every path in this graph either gets to the left-hand branch and finishes, or goes around this loop forever. And if it goes around the loop forever, then we know that we're getting to the point where we're constructing this infinite descending chain of natural numbers, which can't happen. And so this is just like this is a visual representation of the infinite descent proof that we did before. It's not an important thing to say because cyclic proofs will not be an examinable topic in this course. Okay, now let's do a harder example, a much more interesting example, and this was actually proved, I think, by Euclid in ancient Greek times. And the theorem is to say that the square root of 2 is not a rational number. Remember, the rational numbers are those that are exactly expressible as a ratio of two natural numbers. So, you know, a third is a natural number and a quarter is a natural number. The square root of 2 is, you know, somewhere between 1 1/3, 4/3, and 1 1/2, which is to say 3/2, somewhere in between, I think. So to say that the square root of 2 is not rational is to say that there are no two natural numbers x and y such that root 2 is equal to x divided by y. So we can prove this by infinite descent because we're going to assume that there is a counterexample to this theorem. So let's assume for contradiction that the square root of 2 is rational, which is to say that there's a way of writing it as a rational number. There are numbers x and y, which are natural numbers, such that root 2 is equal to x divided by y. Now, just by multiplying out, you can see that this means that x squared is equal to 2y squared. That's a simple manipulation. And you can check all the manipulations that I do in this proof. Now, if I subtract xy from both sides and factor out, then that means that x times x minus y is equal to y times 2y minus x. And that means just by dividing, I have that 2y minus x over x minus y must be equal to x over y, and that's just by dividing both sides. And that means that an x over y is itself equal to the square root of 2 by assumption. So this is a different way, this 2y over x minus y is a different way of writing the square root of 2. And I'm going to define x prime to be the numerator, 2y over x, and y prime to be the denominator, x minus y, meaning that x prime over y prime is equal to the square root of 2 by this displayed equation. And then we can actually notice, this seems like a weird thing to say, but it is a fact, that x squared over y squared is square root of 2 squared, which is 2, and that's between 1 and 4. It's just, I mean, it's a simple fact, but it's true. And that means that if I multiply all sides by y squared, or all elements of this inequality by y squared, and take their square root, then I get that y is less than x is less than 2y. So x is in between y and 2y. And that means that if I take y away from all elements of this inequality, then this one becomes 0, this one becomes x minus y, and this one becomes y. So we have that x minus y is in between 0 and y. In other words, y prime is between 0 and y. But then y prime itself is bigger than 0, and it's just one natural number minus another natural number, which means that y prime is a natural number as well, and so is x prime, by the way, because it's just 2y minus x. So x prime and y prime are both natural numbers, and they have and x prime over y prime is equal to the square root of 2. So x prime and y prime are also a counterexample to the theorem. They're another way of writing the square root of 2, but importantly, y prime is now less than y. So we have, assuming that the square root of 2 is equal to x over y, we have managed to kind of come up with another way of writing it as x prime over y prime, where the denominator y prime is smaller than the original denominator y. That means I could continue this reasoning to find yet another way of writing the square root of 2 as x double prime over y double prime, just by repeating these steps, and I would find another natural number y double prime and x double prime such that the square root of 2 is x double prime over y double prime. And so I would have a counterexample with a still smaller denominator. And by repeating this reasoning, I would find an infinite series of counterexamples such that I can write an infinite number of ways of writing the square root of 2, such that the denominator of each way of writing it is smaller than the last one. Now, again, that gives us an infinite descent on the denominators, which are natural numbers, and that's impossible, so we have a contradiction. So assuming that we have one counterexample, I mean, it has two variables, but we find another counterexample such that one of those two variables is smaller. Well, and always the same one. So the denominators become smaller. That's a contradiction, and so the conclusion is that the original counterexample, square root 2 equals x over y, cannot exist after all, and therefore the square root of 2 cannot be a rational number. So then, infinite descent is one way of thinking about it is a kind of combination of induction and proof by contradiction, and we've seen that it's pretty useful. You can prove some really super interesting things with it. A lot of people don't like it very much. I think students often react badly because this idea of kind of backwards reasoning is somehow non-intuitive. But I think the last thing that I wanted to show is that actually, if you just take the principle of infinite descent and rewrite it in a slightly different way, you can kind of turn it around and rewrite it again as a standard induction principle, which is called complete induction. So complete induction says, to show that something is true of all structures, then show it is true of an arbitrary structure, given that it is true for all smaller structures. So I think what we'll do now is we'll return to the slides and we'll see how to turn around the statement of infinite descent to obtain something which looks more like a sort of familiar induction principle. And then we'll use that induction principle to prove a couple more pretty interesting things. Okay, so here I've written again here the infinite descent principle for the natural numbers to show that p is true of all numbers. It's enough to show that the existence of a counterexample, not p of k, implies the existence of a smaller counterexample. Exists k prime, such that k prime is less than k, and not p of k prime, where k is an arbitrary number. Now, let's just take the premise of this rule and rewrite it using some logical equivalences. So we're just going to use the propositional and first order logic equivalences that we've seen in previous lectures. So here's the premise of infinite descent. So it's just this guy again. And the first thing that I'm going to do is turn this around by remembering that the implication A implies B for any A and B is just the same thing as not B implies not A. So if I do that, I get that not exists k prime such that k prime less than k and p of k and not p of k prime implies not p of k. So that's just by somehow inverting the implication. Next, we can eliminate the double negation from the right hand side just using the fact that not A is equivalent to A propositionally. And now let's look at the left hand side. We know that for any formula A, let's say, then not exists k prime A, so there's no k prime such that A, is to say that all k prime have the property not A. So that means I can take for all k prime not this guy. So if for all k prime it's not the case that k prime is less than k and not p of k prime, then p of k. So that's just using the equivalence that not exists k prime A is the same thing as for all k prime not A. And then let's just write the inside of this a little bit more by observing that not A and not B, well, A and not B is the same thing as not A implies B, because A implies B is false exactly when A is true and B is false. So another way of writing this is k prime, for all k prime, if k prime is less than k, then P holds of k prime. And that's the left-hand side of the implication, and then that's implies pk. And that's using the equivalence that not A and not B is the same thing as A implies B. So this now looks much more like an induction rule, where we show that something holds of a number, assuming that it holds of some previous ones, in fact, all previous ones. And this actually gives us, so if we replace the premise of infinite descent by this equivalent but rewritten premise, then we get something which is called complete induction, or sometimes strong induction. So we have to show that that P is true of an arbitrary number k, assuming that P is true for all smaller numbers k prime. So for all, so our induction hypothesis, if you like, is assuming that P is true of all k prime that are smaller than k. So that's our induction hypothesis, and then assuming that, we have to show that P is true of k, and then the conclusion is that P is true of all natural numbers. Well, think about why this is. Actually, no, let's restate it first. So we pick some arbitrary number k. We assume that P is true for all the smaller numbers k prime that are less than k. That's the induction hypothesis. And then we'll show, as the step case of the induction, that P holds of the number k itself. So we can notice here that there's actually no explicit base case. But in fact, this premise here implies that we have to show that P is true of 0. In the case where k is equal to 0, of course, there are no smaller k prime. And that means that in order to show that P holds of 0, this assumption becomes trivial. We actually don't get to assume anything. We get to assume that P is true for all numbers smaller than 0, but there are no such numbers. And then the conclusion is that P holds for all numbers n. We can see that this premise includes the fact that P must hold of 0. And then we have to show that P holds of 1, assuming that it holds for 0. And then since it holds for 0 and 1, that's all the numbers less than 2, so we know that it holds for 2. And then we know that since it holds for 0, 1, and 2, that's all the numbers less than 3, so it must hold of 3, and so on and so forth. So now let's see a couple of interesting examples of where complete induction can be used to help us prove something, shall we say, non-trivial. So you may or may not have heard of the so-called fundamental theorem of arithmetic. Now, the fundamental theorem of arithmetic says that every natural number can be written uniquely as a product of prime numbers, or sometimes as a product of powers of primes, but that's the same thing. So the theorem is, it actually has two parts. First of all, showing that every number can be written in at least one way as a product of prime numbers, and then the other half is showing that there's exactly one way. So if there are any two ways of writing a number as a product of primes, then they must be the same. Now, the uniqueness is actually much harder to show, but the first part of the fundamental theorem, the saying that there's at least one way of writing every number as products of primes, is not too difficult to show, and it can be shown by complete induction on n. So we're only going to have to show this for numbers that are 2 or greater. So let's assume that n is a number 2 or greater, And we'll assume as our induction hypothesis that every number n prime that is smaller than n can be written already as a product of prime numbers. Then what we have to show for complete induction is that n itself must then be a product of prime numbers. Well, let's consider two cases. First of all, if n is already a prime number, then it is trivially a product of prime numbers. It's sort of the empty product of it's just the prime number by itself is just a trivial product, and so we're done. Otherwise, it's not prime. Remember our law of excluded middle, A or not A is true for every A, so it's either prime or not. So if it's prime, we're done. If it's not, then it must be divisible by something. And so if it's not a prime number, then it is a product of two numbers, not necessarily prime numbers, m and k. And m and k are both less than n. And by the way, I didn't write this down, but we can also assume that they are larger than or equal to 2. We're not assuming we're not writing n as a product of itself and 1. If it's not prime, then it must be divisible by something that is 2 or greater. So in this case, we have that n is equal to m times k, and m and k are both smaller than n, strictly smaller, and that means that by our induction hypothesis, they can both be written as a product of prime numbers. That's just, here we are. And that means that m times k, if m is a product of prime numbers and k is a product of prime numbers, then m times k is a product of prime numbers as well. And we have n equals m times k, so n can be written as a product of prime numbers. And we're done. It's really that easy. Now for our final example. Now this is the so-called Ackermann function, and it's famous in computer science because although you have functions that grow at different rates, so you have polynomial functions and exponential functions and so on, this Ackermann function actually grows faster than any exponential function. So it's worse than exponential in some ways. So there are 3 clauses of the definition. It takes in 2 numbers and returns another number. And this is a recursive function, but somehow the recursion is not quite trivial. So if the first argument is 0 and the second is y, then a of 0 and y is just equal to y plus 1, although I should have written this as a successor of y. Sorry about that. Otherwise, if the first argument is not 0 and the second argument is 0, then we have a of the successor of x and 0 is equal to a on the function x and 1. Again, for 1, I could have written successor of 0, maybe should have. Again, sorry about that. Otherwise, if neither argument is 0, then they are both successors. So the Ackermann function applied to sx and sy is, well, it is the Ackermann function applied to x and the result of the Ackermann function applied to successor of x and y. So a slightly complicated recursive definition there. As I said, it grows fast. And here's an example of just how fast it grows. If I take 2 pretty small arguments, 4 and 2, then the result of a applied to 4 and 2 is 2 to the power 65536 minus 3. So it grows really, really fast. And in fact, it's not completely obvious that the result of a on 2 arguments x and y is always defined, and that's kind of because of this this guy here, or even in this one, you can see that the first argument's gone down, but the second argument's gone up, and here we've kept an argument the same. So I mean, it's not completely obvious that a of x and y is always defined for any x and y just by this definition. You might generate a large sequence of recursive calls, and the fact that these numbers grow so large is exactly because applying a to arguments will generate in like a huge tree of recursive calls. So for this, we're going to use something called lexicographic induction, but it's basically complete induction, but rather than using the ordering on just plain natural numbers, we're going to define an equally good ordering on pairs of numbers. It's sometimes called lexicographic because it's like a dictionary. In a dictionary, to decide the order of two words, you look at the first letter, and if the first letter you order them by their first letters if they're different, and if the first letters are the same, then you look at the second letters, and if the second letters are the same, you look at the third letters and use that to decide the ordering, and so on. So lexicographic for that reason. So we're going to say that a pair of numbers x prime and y prime is less than another pair of numbers x and y, either if the first components are related by inequality, so if x prime is less than x, or if the first components are the same, x prime equals x, and they're ordered by the second components, and y prime is less than y. So that is a perfectly good ordering, and you can definitely check as well for yourself that there are also no infinitely descending chains of pairs of natural numbers according to this ordering. So to prove that a of x and y is always defined, we can prove it by complete induction on the pair x and y. So the assumption is that a of x prime and y prime is defined for all pairs of numbers x prime and y prime that are smaller than x and y. So that's the induction hypothesis. And we have to show, assuming that then a of x and y is defined. And for this, we're just going to consider cases on x and y. And the cases we're going to correspond exactly to the three cases that we have of the definition of a. I'm not going to completely spell it out, but here, for example, we can see that certainly if the first argument is 0, in the case 1 here, then a of 0 and y is always defined. So the case when x is 0 is easy, because a successor of y is always defined. On the other hand, in the case of the third equation here, we have that x and y are both non-zero, and so the first thing to check is that we have to check that this guy, a of sx and y, is defined. And actually it is by the induction hypothesis, because although the first argument of both functions is the same, we have that y is smaller than successor of y. And therefore sx and y is also smaller than sx, sy. And that means that by assumption, a of sx and y is defined. And so since x and this guy are defined and x is smaller than sx, you know that a of this guy is defined as well. So I'll let you to kind of fill in the gaps there, but yeah, so we can show this by complete induction. So now I just want to leave you with a few facts, which I'm also going to leave as like exercises for you to do at home. I already showed you just a few slides ago that complete induction and infinite descent for the natural numbers are equivalent, because because when I state them as inference rules and I take the premise of one, then the premise of the other rule is equivalent just by applying the principles of first order logic. We also saw that two-step induction and one-step induction are equivalent. We saw that at the beginning of this lecture. And in fact, although complete induction looks far more powerful somehow than one-step induction, in fact, they are equivalent as well. So there are two directions to this, and they are done in a fairly similar way to the equivalence of two-step and one-step induction. So first of all, we can derive the ordinary one-step induction principle for the natural numbers using complete induction. So if complete induction is our only tool, then we can definitely get one-step induction back again for free. In other words, if we know that p is true of 0, and that if it is true for k, then it's true for sk, then using complete induction, we can deduce that p is true for all numbers n. But more interestingly, we can also go the other way. If we only have as our working principle, ordinary, one-step induction on the natural numbers, we can actually also show that complete induction is correct as well. So only using ordinary induction we can show that if P is true for all numbers smaller than K, then it's true for K. Then in fact we have P is true for all numbers N as well. And that brings us both to the end of today's lecture and to the end of the material on proof by induction. Hooray! Next time, we're going to begin our final main topic, which is something called modal logic. Now, modal logic in terms of expressivity sits somewhere in between propositional logic and first order logic. So it's not quite so as expressive as first order logic. You don't have the kind of quantifiers and predicates and that kind of thing, but it is more expressive than standard propositional logic in that it lets us talk in a very direct and quite natural way about kind of possible worlds and possible situations. So I shall look forward to that, as I hope you do. Thank you for paying attention if you did, and I will see you again next time. Take care.